Hello, and welcome to this webinar. Let me first introduce myself. My name is Bart van der Zalm, and I am one of the senior engineers at Dynaflow Research Group. At Dynaflow Research Group, we specialize in complex problems in engineering, for example, water hammer, vibrations, fiberglass piping, and finite element analyses. Today's webinar is on using Computational Fluid Dynamics, or CFD, for optimizing multiphase process engineering. Here is an overview of what we'll treat in this webinar. Multiphase flow is a wide field with much theory, much more than we could cover in a single webinar. Therefore, we have based this webinar on examples from our recent CFD practice, and we focus on the lessons that can be learned from them. This applies both to the method of analysis and to understanding the simulation outcome. After 2 case studies, there'll be a live Q&A session in which I'll answer any questions you might have. I hope you're keen to get started, but first off, I will provide you with a small introduction of our company and services. Dynaflow Research Group is an independent consultancy company working with a wide range of clients. Our activities are centered around 2 main pillars: dynamics and flow, and fiberglass engineering. We provide expert advice on how to prevent or mitigate any issues our clients might have in a sustainable way. In addition, we develop software solutions for assessing effects of water hammer and pulsations, and we host various custom classroom trainings on topics related to our consultancy practice, such as the ASME boiler and pressure vessel code. Our company has been around for a long time. It has been founded in 1989. We have more than 400 clients across multiple industries, over 2,800 consulting projects. We're active in more than 55 countries and have 3 offices around the globe. Our main office in Rijswijk, the Netherlands, and 2 separate offices in Houston, in the US, and in Dubai, in the Middle East. Some more information on our in-house software development. 2 packages, Boss Fluids and Boss Pulse. Boss Fluids, you see it on the left, is a search analysis software package. It allows you to simulate the effects of transient events in pipe flow. So the effects on the flow and on the pressure after valve closures, pump trips, filling or draining of a line, etc. And assessing the risks that come about with these flow dynamics. Boss Pulse, on the other hand, is a pulsation analysis package. It allows you to simulate flow and pressure pulsations generated by compressors and pumps. Built into Boss Pulse are API 618 and API 674 compliance checks. Should you be interested in one of these packages, I would recommend you visit dynaflow.com for more information and also find a trial license there. Computational Fluid Dynamics at Dynaflow. The software I've shown on the previous page is based on 1D flow models. Complex flow problems can require more in-depth analysis than these 1D flow models are able to provide, and in this case, computational fluid dynamics is an essential tool. Dynaflow has extensive experience in multiphase CFD analysis, covering various flow regimes, complex geometries, multiple length or time scales, or both, non-Newtonian fluids, and dynamic geometries. Given our experience, we are confident in delivering precise results for any multiphase flow challenge. Let's start with a brief introduction on multiphase flow in process engineering. Multiphase flow is often considered complex because multiple fluid phases can flow together in a variety of ways. This is referred to as a flow pattern. This slide shows flow patterns for a 2-phase flow of gas and liquid, gas with a G and liquid with an L, in both horizontal and vertical setups. Much research has been done in this field. Depending on the fractions of gas and liquid, the mixture flow can settle into any of the patterns you see on this slide. For example, if you have a vertical upward flow with a lot of liquid and very little gas, you tend to settle into the bubbly pattern where you have discrete bubbles flowing throughout a continuous liquid carrier. The other extreme in vertical flow would be a situation where you have a lot of gas flowing and very little liquid, in which you have an annular flow, and the gas tends to occupy most of the pipe with some liquid bubbles dispersed throughout, but most of the liquid is in a thin film around the surface, and the liquid is pulled upward by the high velocity gas flow in the center. These extremes are quite well understood. The in-betweens, so slug flow and churn flow, they have more complicated dynamics. Some of these vertical patterns, they translate well to the horizontal case, but there is also some specific horizontal patterns as well. You can have the most simple situation would be a stratified flow of gas and liquid, which can then develop waves on the interface, or even lead to, let's say, slugs of liquid blocking the pipe, or an annular flow as well. The important thing to take from this is that the dynamics of your process flow are strongly influenced by the distribution of phases throughout the cross-section. So if you have a dispersion of fine bubbles versus a central column of gas moving at high velocity, that completely changes the dynamics of the flow. And the interaction forces between phases and components can also be radically different. This is only for fully developed pipe flow. But in process equipment or in reactors, you can have additional influences from a flow development trajectory, or you can have heat transfer, rotating motion, etc., etc. And this all affects the flow dynamics, so that even adds an additional layer of complexity onto this. Now, in process engineering, the aim is to predict flow behavior based on the operating conditions. Often to be able to obtain correct estimates for heat and mass transfer rates, or momentum loss over a section of pipe, or the residence time of a bubble or a particle inside a pipe. So what you see over the years is that a lot of flow regime maps have been constructed, where you have the flow of liquid versus the flow of gas in this case. If you have a large flow of liquid, you will have a dispersed flow. If you have a low flow of liquid but a lot of gas, you will end up annular, and everything in between. So these maps are often used to predict the flow pattern that you'll have and to choose a corresponding model for the heat and mass transfer rates, etc., etc. It is important to note that different models apply in different flow regions. So some models for the heat and mass transfer coefficient, for instance, you can use for a dispersed flow, but you cannot use for an annular flow. So it is important to classify when which models hold and what flow regime you are in. This classification often hinges on two main categories. One is a dispersed multiphase flow, in which you have particles, drops, or bubbles distributed throughout a carrier fluid. In this case, the interaction forces between the fluid and the particles or bubbles, they determine the behavior and the distribution of them throughout the flow. There are three main mechanisms. The first is flow-to-particle interactions. This is basically a forcing by the fluid onto a particle due to a velocity or acceleration difference, and this induces on the particle forces from drag or a lift force or added mass. In this case, you often consider a single particle, the flow driving the single particle, and then you correct for that you have a big collection of particles. But often the volumetric fraction of particles is quite low compared to the flow. So you only have the flow driving the particles. Other mechanisms are particle-to-flow interactions and particle-to-particle interactions. So these effects occur either in regions of higher concentration, where you have a lot of particles together, or if you have a particle size which is comparable to the length scale of your flow. And these are more difficult to assess, because then the flow forces the particle, but also the distribution of particles changes the turbulence in the flow, which then changes the forcing. So you have a feedback loop, basically a coupled effect. The figures on the right illustrate this well. On the top, you see the turbulent velocity fluctuations in a horizontal channel flow. And on the bottom, you see the particle distribution inside this flow field, where particles tend to cluster on the outer edge of turbulent eddies, and where you have a large particle concentration, the flow itself can be influenced by the particles, and then the feedback loop starts. Flow-to-particle interactions are almost always analyzed. These effects are more difficult, might not be at play, but even if they are at play, a CFD simulation often starts with only considering flow-to-particle interactions and not the two-way mechanism. At the other end of the spectrum, you have separated multiphase flow, where each of the phases occupies a distinct region in space, for which you basically solve the single-phase flow equations, and then you couple them together with an appropriate interface condition. Still, these interface conditions can be quite intricate, because if you have, for instance, a gas flowing over a liquid, the gas tends to have a much higher velocity, and you develop friction at the interface, which you need to model. Usually this is modeled as an effective roughness, but this friction at the interface, it generates waves, and if the waves get too big, then you can also generate instabilities. The videos on the right show this well. This is for research done on a cyclone for two-phase flow of gas and liquid. So the fluid here is spinning, which drives the lighter fluid inwards, so the gas is at the center and then the liquid revolves around it. Now for low concentrations of gas, you see that there is quite a steady column with some waves along its length as it flows upwards. But if you have higher gas concentrations, then the velocity difference between the bulk of the gas flow and the liquid revolving around it can be quite big. And you can have, what you basically see is some kind of bursting of this central column into discrete droplets, and then these bubbles colliding once again to form a steady column. But you have some kind of, this is much more unstable. In the example cases we will treat shortly after, one of the projects we'll treat is considering a dispersed multiphase flow, and the other one is a separated multiphase flow. So all these considerations that we've discussed now we'll touch upon again with a practical example. Now, the benefits of employing CFD as a process design tool. We have seen from the previous sections that the interactions in multiphase flow render them difficult to predict using analytical methods. Often, experimental verification is out of the question as well. So that leaves simulations. Relatively simple CFD simulations can be insightful in the early stages of process development because they capture bulk flow behavior at a limited computational expense. For instance, in this movie, from the main flow at certain operating conditions, we have extracted the torque that is experienced by the butterfly valve as it closes. If the selection of this butterfly valve is very critical for process, then this is very valuable info that you can get from the mean flow without resolving or being interested in all the fluctuations and the transport coefficients and the momentum transfer in every cell. CFD is often associated with full flow resolution, but this full detail is not always necessary or critical for making progress in the design stage or for determining how to optimize performance. For multiphase flow, resolving the full flow is both computationally heavy and requires using complex models for the flow behavior, while from indicators in the bulk flow, you can often already gauge which direction to optimize in. We therefore believe that CFD should be employed more often in process design, and we will illustrate that with two recent cases from our practice. The cases that I'll address follow this exact approach. They start out coarse, really using CFD as a design tool. We'll treat two case studies from recent projects. The first one is a particle distribution in a reactor gas flow. This is a dispersed multiphase flow. As you remember from the previous slides, this is about characterizing the forces that drive particles in a certain trajectory and in a certain distribution. The second case is about mixing of stratified liquids in a storage tank. This is a separated multiphase flow case, where the interactions over the interface are important for the rate of mixing. Let's start with the first case. This project was about a chemical process inside a helical coil reactor. From the image on the right, you can see that the reactor had multiple windings, but we only simulated the first one, plus part of the inlet. The reactor featured a gas flow laden with solid particles, and the objective was to have the particles well distributed over the cross-section to have a sufficient reaction efficiency in the outlet flow. We were not concerned with the particulars of the reaction itself, but just with the distribution of the particles. We were contacted quite early in the design stage, so our objective was to provide an initial advice to optimize the design. Because there was a very low volume fraction of particles, we decided to run a first simulation just featuring flow-to-particle interactions, and then recommended a detailed simulation for a later design stage. In the flow-to-particle interaction, since there is no influence from the particles back onto the flow, we can simulate the gas flow as single phase and use the steady-state flow field as the starting point for tracking particles. So these are the steady-state results for the first winding of the coil. I'd like to point your attention to an important aspect of this flow. What you see here is that the streamlines, they move from the outer to the inner wall and vice versa, which indicates the presence of a corkscrew type movement in the gas flow as it travels along the reactor. What we see if we look at the velocity profile at several cross sections is that in the inlet you have a straight pipe with a fully developed flow, which means that the velocity maximum is in the center of the tube. As you enter the helical winding and we make a cross section at 90 degrees, you see in the velocity profile that the point of max velocity has shifted to the outside. So you have an asymmetric velocity distribution. What that means is that if the velocity is maximum here and lower here, and velocity and pressure are coupled, that means that the pressure at the cross is low and the pressure here is relatively higher. So you get a secondary flow from the point of high pressure to the point of low pressure. This is quite common for flows in circular patterns, which means that in the cross section you actually have distinct cells, a secondary flow of distinct. This movement can be considered beneficial for mixing if powder particles are small enough to be regarded as tracers. The trajectory of larger particles is strongly determined by inertia. As an analysis of the particle forces, we found that the two most important aspects were opposing each other. So the helical geometry induces a centrifugal force on a particle, which scales with the streamwise velocity. So if the particle has a streamwise velocity v theta, and it's basically going around the center point, you'll have an outward centrifugal force on the particle. And then turbulent fluctuations inside the gas flow result in a net particle transport from regions of high concentration, which is usually near the wall because the particles stagnate there, to regions of low concentration, so the core flow. What we then did with analytical models is to quantify the order of magnitude of these forces and investigate their ratio. So the ratio of centrifugal forces to turbulent fluctuations scales with the density of the particles over the density of the gas, which for dispersed multiphase flow is often an important parameter. In this case, the gas density is about 1 kilogram per meter cubed, whereas the density of the particles is 2,000-fold of that. So this factor is definitely in favor of outward motion. And then from here you can basically gauge that, the particle diameter and the mean gas flow magnitude, they are both squared. They favor So larger diameter particles and a higher velocity favor outward movement, whereas a larger radius of the coil reduces that effect, and the turbulent mixing scales with turbulent velocity fluctuations. So these are the important factors at play: the diameter, the ratio of the coil, and the streamwise velocity. If you look at the effect of these parameters, so let's say for given process conditions, and look at the effect on the particle distribution for certain diameter particles, this is what we found. So if you have 40 micron particles, the order of magnitude of this ratio, centrifugal to turbulent, is about 3.4, and we see that the particles are mostly concentrated along the outward edge, which indicates that centrifugal forces push them outward and the turbulent forces are unable to push them in. As the particles near the wall and their velocity goes down, they will also stagnate and end up more along the bottom of the cross section. Now for 10 micron particles, you see initially it's already distributed more evenly over the cross section, and you can see very well this distinction of these separated flow cells, as was also visible in the steady state flow. So for given process conditions, depending on the diameter of the particles, we get wildly different results. Just because for the 10 micron particles, the centrifugal forces are on the same order of magnitude or lower than the turbulent fluctuations in the gas, whereas for 40 micron particles, centrifugal forces are much larger. Now, there are some notes that you could make here. If you look at the results for the 40 micron particles, since the centrifugal force pushes them outwards and they all cluster near the outer wall, that means that both the distribution of particles will locally change the turbulence in the gas, and that there is a much higher probability of particle-to-particle interactions changing the individual particle trajectories. That is all true. So in that sense, this simulation, only considering flow-to-particle interactions, is quite coarse. But the important takeaway from this is that the chances of, for given flow conditions, having these particles uniformly distributed throughout the cross-section is highly unlikely for 40 micron particles, whereas for 10 micron particles, if you also take into account particle-to-particle interactions and change turbulence along the outer wall, you could sense that that would already be more probable. That is already very important for our client. So the bulk behavior of the flow, you can already draw conclusions on that. Using a limited complexity CFD model to start, we showed that centrifugal forces tend to overpower the mixing effect of the turbulent gas flow at the given process conditions. These simulations gave our client an early sense of direction for optimization, which was aim for smaller particle diameters or aim for a lower gas flow rate, even though lowering the gas flow rate, so lowering the mean velocity, reduces the effect of centrifugal forces but also reduces the turbulence intensity, or aim for a larger coil radius, or a combination of all three. We gave these points as advice to our client because the optimization they had to do was also a trade-off with other factors of importance that were outside of our project scope. But the result of our simulations can highlight crucial process parameters early on to a design team, and that is important. Our client here in this case decided not to pursue the project further because they wanted complete flexibility in particle diameters while maintaining set flow conditions. And from our ratio of forces, you could already tell that that was very difficult. So we advised them to change to another reactor geometry. So, on to the second case study, mixing of stratified liquids in a storage tank. This is a separated multiphase flow example. In this project, we had a large storage tank filled with two liquids that were of a similar density and miscible. The client's objective was to continuously recirculate the liquids in this vessel in order to end up with a fully mixed end result. The initial estimate was that there was a long timescale involved that could not be efficiently simulated with a fully resolved CFD. So our method of analysis for this project was to employ a two-stage approach. Because the fluids were of similar density, their mixing would not really affect the density for the flow calculations. So what we did was a steady state velocity field simulation for a single liquid, resolve the turbulence fully there, and use that steady state flow profile then to solve a transport equation for the concentration within the fixed flow field. So for the timescale considered, the flow field will be roughly similar irrespective of the concentration of both liquids in the inlet. It's also important to note that our advice on the total mixing time has the same order of magnitude as a margin, right? So 30 minutes or so, and complete precision is not required. So this legitimizes the use of this two-stage approach. So you lose a bit of detail, but this allows you to efficiently simulate a very long time scale with CFD, and the end result can still be a worthwhile estimate for the end client. For the recirculation in this vessel, the concentration in the outlet is linked to the inlet by a cyclic boundary condition, and the initial distribution of liquids is stratified with a heavier fluid on the bottom and the lighter fluid on the top. So the inlet is an internal jet nozzle oriented at an angle, and the high velocity exhaust promotes mixing in the vessel. The nozzle creates a free jet that induces a steady flow throughout the entire tank. Right, so there's one high velocity jet, but that creates a motion even far away from the jet in the entire tank in a steady state. Near the jet, there is a large velocity difference between the jet itself and the quiescent fluid that it is issued in. And you have mixing by two mechanisms. Right, so you have advective mixing, so you're basically replacing fluid of a certain concentration with fluid of a different concentration in the jet, just purely by advection, which then scales with the mean velocity. But also along the edges of the jet, there is a lot of shear, and you get turbulent mixing. And there you have a large transfer of momentum from the high velocity jet to the low velocity tank fluid. But analogously, you also have a high transfer of concentration in that region. And actually, as the jet progresses, it also entrains liquid from the outside and then broadens. So you have two mechanisms. One which scales with the mean flow, and the other one which scales with a diffusion coefficient, which is more or less related to the turbulent fluctuations. So near the jet, there is a lot of mixing, and away from the jet, the mixing rate is relatively low. So this is a slice through the flow domain of step 1 of the CFD, so the steady state velocity field for a single phase fluid. So the jet actually creates a recirculation pattern throughout the entire tank, right? So it issues fluid at a high velocity upwards, and then you get a big recirculation cell here and another recirculation cell here. And this steady state flow field throughout the tank, we then use to consider the effects of concentration and mixing over a very long time scale. So in this simulation, we resolve the pressure and the velocity in all three coordinate directions. Those are linked, and this simulation takes quite some time to run for a domain this big. But when we consider the concentration only, we basically consider a single scalar parameter, and it is much less computationally intensive to have a simulation run for hours by just iterating on one parameter. So that's step 2, solving a transport equation for the concentration. So the mixing process is simulated with an advection diffusion transport equation, which takes into account the two mechanisms we have just discussed. Advective mixing, so replacing fluid of some concentration by fluid of a different concentration by means of the mean velocity in the jet, and diffusive mixing, which is basically by turbulence in this case. If you consider the volume fraction alpha of liquid A in each mesh cell, then basically the time rate of change in alpha depends on the advective mixing, which scales with the velocity and diffusive mixing, which scales with the gradient in alpha and a diffusion coefficient. Normally you would know this as the molecular diffusion coefficient, but in this case diffusion of concentration by turbulence is orders of magnitude larger than the molecular diffusion. So what you normally do is that you use a turbulent diffusion coefficient in this case. Now this partial differential equation is a linear equation for one parameter, alpha. So this equation is both faster to solve than the full fluid dynamics equations, and it also allows for a larger time step because there are no nonlinearities. And that means that it's much easier with this equation to solve a period of multiple hours to see whether or not you converge to a fully mixed tank. Our client's criterion for mixing was that throughout 99% of the flow field, the mixing ratio in each cell would be 75 to 25. So to this end, in our CFD model, we have modeled a series of probes distributed, which samples the value of alpha over time. And then if you consider the average over all probes, you can calculate a bulk convergence percentage. In this graph, you see that over time, you steadily converge towards the mixing criterion set by the client. There is no time scale here, but it's important to know that convergence to the mixing criterion is on the order of hours and not days, or also not minutes, right? So this provides the client with a sense of range. Takeaways from this case is that a two-stage simulation approach allows for detailed long-term calculations on a relatively steady flow field. In this case, possible approaches for optimizing the mixing rate would be to adjust the orientation of the inlet jet nozzle. It had a fixed orientation in the simulations we did, but you can imagine that its orientation is a parameter of influence for the mixing rate. Increasing the jet velocity, which would influence both advection and also the turbulence intensity on the edges of the jet. Another factor of influence would be to optimize the location of the outlet with respect to the inlet. In this project, these optimizations were not further analyzed because the client was already satisfied with the initial estimate of the total mixing time. It aligned well with their expectations as well as with the window they had available. Implementing the flow rates recommended in our simulation therefore only required very limited changes to their process. So these were the two case studies I wanted to discuss. I hope they were interesting and gave you a sense of understanding of how to approach complex multiphase flows from a practical engineering standpoint. That often requires assumptions or simplifications made beforehand, splitting the problem into multiple segments in order to make it tractable. And then you're not going for the full, complete detailed flow, but you're going for bulk behavior, which gives you at an early stage a good idea of how to optimize your process or how to design your process. And if that's what you're after, then doing CFDs very early on in the process is definitely recommended. We will now transition to a live Q&A session in which I can discuss any questions you might still have. So up front, I want to thank you for attending this webinar. We have multiple webinars coming up in the future, so be sure to visit dynaflow.com and register for future webinars. The live Q&A will last about 15 minutes, and afterwards please hang around because there will be a brief survey. The responses to this survey help us shape future content and product features. After this webinar, a video of this presentation will be shared, so please forward it to any of your coworkers, colleagues, or friends you think would be interested in this content. I hope to see you at our next session. Thank you very much.